Alright, CNT125, Chapter 9, we're on the section on routers. So I had a couple homeowner routers here to jog your memory, and then a couple commercial routers that might be in a facility. Jog your memory here. A router is really designed to connect two or more networks and pass packets between them. I hate to say it this way, it doesn't really care where the nodes are, it's really interested in the networks, getting the traffic to the right network. These two networks could be two Ethernet networks, or could be Ethernet to a provider network, or something different. Our router connections are typically from the LAN to the WAN, from my network into a WAN connection or a WAN provider kind of thing. Routers are responsible for determining the best path from, from this network to other network, so it needs to maintain information on that. Here's a picture I showed back in 120, jogging your memory. Routers are really responsible or really interested in reading the packet's IP address and getting the data from, through the series of networks to the correct network. And once it's there, this router over here, if you will, would be like, okay, I'm done. I've gotten the data to that network. I'm done with the job. Switches, remember, are reading layer 2 addresses, typically, MAC addresses. So the switch at that site is like, I got it, router, I'll take care of it. I'll get it to the right node. So the router is really interested in getting data to the correct network. The switch is now interested in getting it to the correct node at that site. I used the example back in 120 of routers are going to get it to, the York campus of Hack, as opposed to the Gettysburg campus. And once it's in the York campus, the router's like, I'm done. The switch will now read the MAC address and go, okay, I'll get it to the correct computer at this site. Thanks, router. So keep that in your brain to help with understanding the router and switch dynamic here. The router itself has internal processor, operating system, memory, input, output, etc. And might even have multiple slots. Here's, if I tear a cover off of a router, I'm basically going to find it's a specialized computer. It doesn't have the monitor, keyboard, and mouse ports, but it really does have the, it's kind of like a computer motherboard, if you will, with your RAM, with your ROM, with your RAM, with your processing, and some storage. And there's multiple interfaces, multiple NICs, if you will, to move data in and out. Side story, you can actually build a router out of an old computer that you snap a couple NICs in. All you would need to do is load a router operating system on top of it and turn it into a router. There is out there Linux-based routing operating systems that are free to download that you could install on an old computer with a couple NICs in and turn it into a router. So just kind of getting you thinking, it's really just a specialized computer to move data through. Here's the routers we have in our lab room. If you look closer at them, we typically have some LAN ports over here. We might have some WAN modules over here, kind of thing. These are typically the ports we use in our lab room to go, from our network to another network, kind of thing. And by now, hopefully, you remember the console ports on the back on the 2011, if you will. So all routers can actually do these things: connect different networks, LAN to WAN, interpret layer 3 and even layer 4 addressing, port numbers, if you will, determine best path, and even reroute traffic if a path is down. As it builds a table of networks, it can always, when a network's down, find another path and use that path. Routers may be able to perform any of these functions in addition, all depending on the capability of. Filter certain traffic, do simple firewall functions. We're going to do that later this semester. We'll write some firewall rules. Do local and remote connectivity, allow remote connections in. We'll do that later this semester too. Provide some fault tolerance through redundant components such as power supplies. Some of my larger routers, I can actually buy some redundant pieces of equipment put in there. Monitor traffic and report statistics. We are going to do that later this semester as well. Diagnose connectivity problems and trigger alarms. Again, we're going to do that as well later this semester. So there's a lot of additional functions that our commercial routers can do in networks. All we need to do is kind of enable them or configure them. There are some different router categories: core, interior, and then as well the exterior. Core interior routers direct traffic between networks within the same autonomous systems. Autonomous system is a group of networks often by the same domain operated by the same organization. So you can think of all the routers and so forth that Hack owns to route data between. That would be an autonomous system. And typically there's a number associated with that as well. We'll see that when we configure routing protocols later. So there's the core routers in a company, core routers in a company. There are edge routers. This would be probably the sole router at the edge of the company that connects your LAN out to WAN, if you will. That might be the sole router unless you do some redundancy and have two routers working to do this job. But that is typically the router at the edge of the company that's going to connect your autonomous system with an outside network, use your provider network. Your exterior routers, these are the ones that your ISP, your network service provider, is using to basically move data across the internet backbone. These would be the ISP type routers moving traffic between, our LAN, some other company's LAN, this school's LAN, that school's LAN, moving all the traffic between them. Our homeowner routers that we have at home are usually kind of plug and go. I plug it in and I might browse in and do a couple settings, but it's usually browse it and point and click a couple things to change some settings. Our commercial multi-protocol routers like we have in our lab room are going to require us to literally console in, write a series of commands to get it to do certain functions. And we'll end up having configuration files with a variety of things in there that we're turning on and configuring. Routers maintain a routing table. This is basically a database of networks and where they're located. It will then consult that to know, oh, I'm going to pass it this way. Oh, I'm going to send it that way. Think of this very much as like a mental map that you have in your head. A lot of people, once they've lived in an area for a while, might know multiple different ways to get to fill in the blank. Work, the grocery store, gas station, etc. They might know multiple ways, and they do because sometimes there's too much traffic, sometimes they're doing construction, sometimes there's a train going in that part, you have to go around. So you do the same thing. You have oftentimes more than one route to get somewhere, and you even consult that sometimes before you leave your house to say, I'm not going to go this way, it's too trafficy, I'm going to go this way. I can usually get there quicker if I go this way. Routers are doing the exact same thing. They're building a table of networks where they're located and how to get to them, and they can adjust those based on changing dynamics in the network. And that's where your routing protocols come into play. The routing table contains IP addresses and network masks to identify where these networks are. We will look at routing tables in a little bit when we do our routing protocols. So the router would have a table of, this network here, this network here, this network here, this network here. This router would have that in there to know, am I going to pass it this way and over, or this way and over, or just simply out this port? So it'll start learning, this network, LAN B, LAN A, LAN C, LAN D, where are they located, and how can I get to them? If it's this router here, it would know I can pass it this way, or I can go boom, 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 and get there. I would have two paths that I could use. Static routing, dynamic routing. Static routing is just that. It is a static one route, if you will, that gets used. Sometimes network administrators will configure a static route between maybe my LAN and the ISP. Maybe there is only one way to get there, so why have the router do all this constant update and maintenance when there's only one way? So you might configure that in the router, say, hey, anybody's trying to get to, the WAN, if you will, boom, here's your route, go this way. Meanwhile, in a network where I might have multiple routers and multiple networks, maybe this is, Harrisburg, Hack's Harrisburg campus, and these are all different buildings. I might be using routers to move traffic between these buildings. Well, in that case, I might use some dynamic routing, because if this link breaks here, this router can say, oh, I'll just send traffic this way as opposed to this way, or whatever. There would be more than one way to get somewhere then. So dynamic routing is it's going to calculate its path and maintain that, and if something changes, it will kind of update that in the table, saying, no, don't go that way, that's closed now, or that's broken, go this way and go around. That's where your routing protocol comes into play. There's various different ways you can look at a host routing table. If I'm on a workstation from a Linux and Unix workstation, I can use the route command. It'll show the routing table on that host. Windows, I can do route print. On our Cisco routers, we're going to do this a lot. We use the show IP route command. That actually says, let me see the routing table that you have learned, that you have compiled. We will do this a lot as we work with our routers and routing protocols. This is a way to see your routing table. Show IP route. Show IP route. Here's a sample for on a Linux machine. Here's a sample on Windows host. And then here's the sample on an actual Cisco router, showing the networks it's learned. Here's the networks it's learned over here on the left. Over here on the right is kind of like, all right, pass it out this port. If there's an intermediate step to this IP, like these guys right here, and then it maintains a table of, hey, it's one network away, one router away, if you will, depending on the protocol, or depending on the routing protocol is the metric it keeps there. And that's what it consults. I know these networks and how to get to them. All right, routing metrics. There's a number of different ways that routers maintain maintain information about paths. We do the same thing. We have different metrics in our brain of, hey, this is a highway. I can usually go, 65 on here. I can get there pretty quickly. This is a back road. I can't do that. I can go 45. But I know the back road at this time of day has less latency, less delay than the highway, because the highway gets clogged up with traffic. So we have different metrics in our brain that we consult just to drive from A to B. Routers do the same thing. Different routing protocols use different metrics, and those metrics help it decide, oh, this is more routers away than this one, so I'm going to use this second path that I learned that's less routers away. It's got to be a better route. Bandwidth, delay, load, maximum transmission unit, routing cost, that's usually a number assigned, reliability, network topology, etc. Depending on the routing protocol, it uses some of these, maybe one of these, some of these, and some routing protocols actually combine a couple. And that's kind of what our brain does. We usually combine a couple. We look at time of day, we look at, the type of road it is, whether there's construction, whether there's a special event going on, and then we use that to make our decision on which way we're going to go. Routing protocols used by routers to communicate with each other to help determine best path. Well, the routing protocols build routing tables. So this routing table we looked at back here, a routing protocol helped build this, and it maintains that and updates that as things change. That's what your routing protocol is doing. We do the similar thing. We might either listen to a traffic report on a radio, or we might actually pull our phone up and look at our, maybe Google Maps or something and see, is there any delays in this particular area? I might go another route to go around it. Routing tables in the router are doing the same thing, as communicating that information and updating its tables. Routers rate the reliability and priority of a routing protocol based on these criteria. Each routing protocol is going to have an associated administrative distance with it. The administrative distance is kind of like the reliability or the quality of that link, if you will. If it has a administrative distance of 0, that's excellent. It's like directly connected. You can't go wrong. It's right here. If it has a really high number, that means it's a path that is broken or really, 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 really slow. Avoid that. So any routing protocol is going to have an associated administrative distance with it, showing kind of like the reliability of that information. Convergence time is the amount of time it takes a routing protocol to update to a change in the network. Some of our routing protocols are slow to converge because they literally need to pass the information from router to router to router to router. Other ones literally send the information to all the routers at the same time, so they're much quicker to update when a problem occurs. Overhead, some routing protocols literally put a lot of traffic on the network consistently to update information. So it's consistently adding chatter, data onto the network. That is going to add some overhead to the existing data that's already there. Certain protocols do that. Here is a summary of a bunch of the routing protocols the book talks about. We'll come back in the next podcast and start working through some of these common ones, especially the common ones we're going to use in our lab room.